In Release 2.0 of CompactSections, a method for doing Cozzone's solution for unsymmetric sections was added. So before you can apply this method, you've got to create your section and then apply a material, and then it has to have a mesh. So the limitations of this method, it applies to sections oriented about the principal axis. It's not you can't apply any neutral axis to the section as you can with a numerical method. You can only apply it to a section with a single material. And as I said, there's a numerical method for doing the general solution, and that was released in version 1.0. So in the material definition, you have to define the yield stress for tension and compression, the ultimate stress for tension and compression, and the Ramberg-Osgood parameters for the longitudinal grain direction for both tension and compression. So now I'll just do a quick walkthrough of the theory. So what we need to do is the same as the Cozzone's method for symmetric sections, is we have a true stress variation down the section. And in the unsymmetric case, we need to find the F0 value for the top and the F0 value for the bottom. And we're going to make use of a simplified assumption that the strain is linear, so plane sections remain plane. So if you were to look at the stress strain plot, you've got your true stress strain plot. And then for the trapezoidal stress variation, we have this imaginary F0 stress at where the strain is 0, and then it's linear up to the Fm value. So the goal is to find the F01 and F02 such that the true moment from the true stress variation equals the trapezoidal moment. So having a trapezoid makes it very simple. So we have this F0 value that goes, now right now I'm just talking about, say, the top half, or the bottom half, but let's just say the top half of the section. You have your F0 value, and you have it, which is rectangular, and then you have a elastic variation from the neutral axis up. So if the moment for this plastic area, the F0 value is constant all the way up, so that's the integral from 0 to the top of the section times y dA, which is this, and this value here is just first moment, q. So it's F0q. We're talking about this portion right here. Now for this elastic portion that's triangular, the stress is proportional. It's going to go from 0 up to Fe, so that's simply y over c. C is the height of the section. So the moment about this base point here, this neutral axis point, is the stress times y dA. And the stress is varying from 0 to Fe up the section. So we plug that in, and then we pull out the Fe over c, the constants, and we have this y squared dA integral, and that's I. So this is just simply Fe times I over c. And you could also, since Fe is, if you go back up here, is Fm minus F0, we have the moment of this elastic, I'm calling it the elastic moment, is this value here. So the total moment for the top or bottom portion is the sum of the plastic and elastic moments, and that can be written like that here. So if we divide through by I over C, we get this MC over I is equal to Fm plus F0 times this term here, which is called K, minus 1. And this term is denoted by FB, which is a fictitious stress. It's also called the modulus of rupture, and it's this term here. So the steps that need to be performed, first you need to locate the neutral axis on the section. And by default in the program, it's the elastic centroid. And then giving a compressive or tensile strain, we have a strain distribution. And the strain is not going to be the same on the top and the bottom. But we assumed it's linear. So if we know one strain, and usually it's, in the program you have to give a compressive value, and you might get that allowable compression from a local buckling value for a web, or anyway, you've got to come up with a compressive allowable. And then the F0 and F02 are computed by a numerical method. It was developed by Tanabe, and you can find that if you look at the first Cozzone's method video, you'll see a walkthrough of that method. It's a little more complicated. So these values, it's going to be computed off using the Ramberg-Osgood curves for the tension and compression. And then the program will compute K for top and bottom. So the total moment is the sum of those two solutions for the compression portion and the tension portion. And that's it. It's not that complicated. So now we'll go and solve a problem in the program. So here we have a section, and this is taken from Brune, section C-8. And we've applied a material. Let's go, you see the material is 7079 T6, so let's go look at that. It's this guy here. So you'll see that we've defined for longitudinal values, FCY and FTY, which is the yield allowables, and then also the ultimate allowables for tension and compression. And over here are the Ramberg-Osgood equations. For L is longitudinal, the exponent, and the strain offset. And there's two portions of that curve. It permits for two different exponents. One up to the strain offset, and then from the strain offset up to the ultimate. We need values for longitudinal and compression. So once that's done, we simply go to computations. Underneath Cozzone's method, you'll see one called Unsymmetric section. So here we have the method for Cozzone's plastic bending analysis of unsymmetric sections, and it says rotate the section so that the principal axis is horizontal. Tension is assumed to occur on the top portion, and it says the section may not be symmetric. So the y-coordinate of the neutral axis, that's defined as default is and up here is 0, it's negative value going down. So the default is the CG. And the allowable compressive strain, and let's say we came up with a value, and I'm going to use Brune's example here and solve it. And you see down here we have the tensile strain, which is computed simply by knowing that we know the value down here is 0.009, and the value, and it's a linear variation through the neutral axis, which we said was the centroid. And we got a moment capacity of 17,912 inch-pounds. And we also compute the shear correction factor. So how do we know that's right? Well, the 17,900 is close to 18,000. If we go over to section properties and go to plastic, you see down here moment capacity. That's 17,800. So it's pretty close. And then that is simply the section modulus times the yield stress. We can also check it by going over here to the plastic analysis. Let's give it a load case name. And then in the neutral axis, we're saying is 0. And we want to add a critical point. So if we go, the bottom of the section is -2. And the midpoint of that section really doesn't matter, but to say 0.3. And the allowable strain is 0.009. Click OK. Oops, that's got to be a negative because it's compression. Okay, so we've got a critical point, which is going to derive this solution and solve it. It checks itself. Now here you see we get a value of, it says the point, it computes the neutral axis, and it says it's at -0.37, which is very close to the location of the plastic centroid. And here we get a value of 18,000, which is within 150 pounds of what we computed before, 200 pounds. So let's go back and let's use, say we got 18,000, and the neutral axis location is this value here. And let's go back to our, and we're going to put that back in there, solve it. And now we get a value that's very close to what we got from the numerical solution. So that kind of sums it up. It's just another way of cross-checking results. And please contact us if you have any questions. We can do a remote session if you'd like, and hop on your computer and help you if you have problems. Thanks for listening.